Okay, so let's go and get started today. So in this session, I'm going to try to go over some more things about meshing, some different ways you can kind of go into meshing, and some different ways that you can kind of make a mesh finer if you need to in certain areas. So I think the last time we talked about meshing and how, obviously in areas of curvature and stuff, you want to make sure, your mesh is actually kind of mapping the area properly. So if you have like areas like that, you may want to go in and, maybe make the mesh finer. But then sometimes you start running into the problem when you do that so if you make the mesh finer in the entire part, then when you really only need to fine mesh in this kind of one area, what ends up happening is obviously you're going to increase your simulation time for pretty much the entire model when you really don't need to. If you have a decently fine mesh here, and you have enough elements across, you really don't need to have a very, very super fine mesh everywhere if there's only one area that you're kind of concerned about. So that's what I'm going to kind of go into today. A couple different ways that you can kind of make kind of a finer mesh in the actual areas where you want the mesh to be finer. Okay, so pretty much the first way to do this is something that's called mesh controls. So mesh controls, what I did, this should be familiar with this from last time, but so static 3, I'm just going to edit this study. I think this was a pretty fine mesh last time, but I'm going to kind of modify it and kind of show how to use mesh controls. So what mesh controls pretty much do is it'll allow you to actually select different areas that you want to finer mesh. And what SolidWorks will do is it'll actually go in and based on your settings, it will actually make a finer mesh around that area. Which this can be very, very useful when you're dealing with, especially areas that are curved like this, or maybe holes, where you have a change in geometry, but only in a localized region. The whole part is not, curved or something like that. So how you pretty much do this is, again, this study is just a copy from a previous study. This is the same study from last week. So what I'm going to do this is, so under mesh, well, let's just look at our mesh here real quick. If I just go create mesh, I think last week this was a lot finer. I just kind of brought this back to kind of an intermediate mesh. I'm going to leave everything here at default, just the default blended curvature based. So I really don't have to do anything here. So I'm going to cancel this for a second. So how you actually do mesh controls is if you actually right click on your mesh, what will happen is this little dialog will appear, and then what you can do is you can do this option right here, apply mesh control. This is actually pretty simple. It looks very similar to the actual mesh. And so what you can actually do is when you're actually in the mesh, or in the mesh control, I should say, you can kind of adjust this. You don't really have the blended curvature or whatever. It's still going to pull that from the actual default mesh that you're using to mesh the part. But you can kind of adjust the mesh density. So if you want something that's a little bit finer, or also if you want something that's a little bit maybe coarser, you can also do that with a mesh control. It doesn't just have to be used for fine. So in this case, obviously, we've got this area here that we probably definitely want to, what's the word? Apply a little bit finer of a mesh. So what I'll do here is just kind of crank up the mesh here. I'll go like really, really fine. It's fine. It's not a really complex part. And then what I'll do is I will go ahead and just select this area right here. And just to show it as well, I'll also select these holes. Again, in this simulation, it's not really going to matter because this entire back face is fixed. The force is getting applied here, so the holes are really not going to deform probably hardly at all. So we're really going to be looking at this, but I'll just kind of show you what the holes look like, just so you can actually see what mesh controls kind of do. So kind of crank that up again, just like the regular mesh. You can go in here and actually adjust the sizing to whatever you need if the slider is not getting you the right values. So based on that, what we can do is I'll just go ahead and hit accept. You can also do, I think you need to create mesh here. Let's see. Okay. You can do something like that too. But what I'll do is typically if I go back into the mesh controls, under this control, I'm going to rename this as 1 because I was setting up a study earlier. When you set up a study early and you have a control, even if you delete it, it'll still call the second one as 2, although there's really no 1. So when you go back in here and just do edit definition, so typically what I'll do, select the faces you want to do your mesh control on, just hit accept. And then what you'll see is these little kind of like little pink or kind of pink dots or pink or purple dots all over those faces that you want to actually apply the mesh control to. So then what you can do is then you can kind of proceed meshing like you normally would. So we can go here, we can go to our create mesh. And then in this case, since I've made these fine, I don't really need to crank up the entire parts mesh to really, really fine. what I can literally do is just kind of keep this in the middle. I could go even coarse, but I'll just kind of keep it in the middle. So we're gonna have a coarse mesh everywhere, or like a intermediate mesh, I would say, everywhere. And then on these faces here, you're gonna have kind of a fine mesh. You won't really see the mesh just after you do the mesh controls. You'll have to actually do this to actually see what the mesh controls did. So what I'll do here, I'll go ahead and hit accept. And now you'll be able to see once this finishes. Okay, so now you can see what that does. So you can see where we have a really, really fine mesh now around this area. And you can see where it'll starts fine, and then you can kind of see how the elements kind of grow back into the normal mesh size. Same thing with the holes. Again, in this one, the holes don't really matter too much, but you can obviously do that with holes. A lot of simulations, holes are a big one where if it's a bolted connection or something, if you've got a bolt in there, yeah, you probably really, especially since it's curved, you probably do want to have a finer mesh there because that may be an area that you want to look at. So, um, so then that's pretty much how you do the mesh. And then any questions so far about mesh controls or meshing in general? Okay. So then pretty much once you do your mesh control is very, very easy. Then after that, literally you create your mesh, you have your mesh like this. Everything else is exactly the same of the process. Nothing changes really. So all you have to do now, once you have your mesh, you've got this mesh now that you've kind of customized, I guess you could say, with the mesh controls. Then all you need to really do now is just go like you would normally would and just run your study. And then you'll obviously get your study like that. And you can see, so how quick the study actually ran, if you recall, probably from last week, when we did the really, really fine mesh, it took probably maybe 10 seconds or something to run. Now it literally ran with probably within like 1 or 2 seconds. So we've actually cut down on quite a bit of time. And obviously, obviously when you have the big one, or the, what was I going to say? When you have the entire part that has a very, very fine mesh, you're wasting a lot of simulation time on a lot of these elements up here and maybe over here. When you're really interested in, the stress, probably in this region for this part, obviously. So when you do that, you're going to get a very similar result by using the mesh control, but then you don't have to really waste a lot of that simulation time. And this can be very, very drastic if you're dealing with assembly simulations or even just really complex parts. You can end up taking you hours and hours to run simulations. So being able to kind of do mesh control, if you really need something fine in one area, and just being able to say, I want everything to be just a decent quality mesh or a decent, like I guess like an intermediate mesh, like over most of the things. So it's a decent quality. You don't have to really deal with too much problems. You have enough elements across the thickness. But then when you want to come in maybe to certain components or certain areas, typically like in a part or something, then that's where mesh controls are really, really useful. So yeah, so that's really nice. So then the next way you can do, any questions on mesh controls or running simulation with mesh controls? Okay. So the next way you can do it, so this is one way, obviously. Another way is something there's something in simulation that's called adaptive methods. And there's two main methods that you'll use. There's really two. So what I'll do here is I created another study that's called H-adaptive, and I'll kind of go into what these are in a second. So this study was a copy of Static 3, literally. So I just made a copy here. I've not changed anything yet. There are no mesh controls. This is a copy of Static 3 before I started doing any of the mesh control work. So if you actually go to if you go to where the study is actually, the name of the study, you can right click here and you can actually go down to properties. This is a good area to go into. There's a lot of information about the study and how you can kind of play with different things in the study. So when you're dealing with stuff like this, again, the first sheet options, I think I talked about this a little bit in the first session, a large displacement. So if you have a study that is still static, all of the, what is it called? All of the assumptions are correct, but maybe it's displacing a lot. Maybe it's like a rubber part or something. And let's just say whatever material you're using is linear and everything, but it is displacing quite a bit. It's not plastically deforming or anything. You can actually use this large displacement because, again, one of those assumptions is when you want to have small displacement relative to the model. So if you have large displacement relative to the model, but all the other assumptions are still holding true, you can come in here and do large displacements. which will actually gives you a more accurate result when you're dealing with something that's displacing quite a bit relative to the model. Again, this does not mean anything if the material is not linear elastic, and all the other assumptions are, if any of the other assumptions are false, this large displacement is not really going to help you too much. But if they are true, but you are getting like an error, sometimes you'll get a warning about large displacement, and sometimes it'll actually just say, do you want to turn it on or off? That's the same thing as clicking this box here. But again, if you're getting something like that, again, you want to make sure that you're not plastically deforming the model. Okay, so from there, when you get into adaptive, so there's an adaptive tab here. There's some other tabs. I won't really talk about most of those, but so the adaptive tabs, by default, you're not using any adaptive methods. So pretty much what adaptive methods are is it's a way of actually adjusting the mesh as it runs the study. And so it's kind of to give you more accurate results without having to, what's the word? Without having to kind of go in and, have to make a really fine mesh or something. It's kind of some different ways that you can kind of get a finer mesh or I wouldn't say finer mesh, get a better mesh for your model without having to make it just really, really fine. So the first one I want to talk about is H-adaptive. I'll kind of summarize what each one of these are. So H-adaptive, H also, a lot of people designate H as the element size. So H-adaptive, pretty much what it does is as it runs the study, it'll do several iterations of the study. And what it'll do is wherever it detects a high area of stress, what it'll do is it'll come back and it'll actually find the mesh in that area. And then it'll run the study again. And it'll keep doing this until your stress is kind of going up, until your stress is going up like this. What it'll do is it'll try to do that until it kind of plateaus out. And it converges. Obviously, if it keeps going all the way up, then you probably have a stress concentration. This is not going to really help too much. But what it'll do is it's kind of like it's kind of like an automated way of applying a mesh control in one study. So instead of you having to apply it and then kind of go back and say, maybe I want it a little bit finer, the H adaptive will be kind of applying it automatically in the areas where it feels it needs to. So this is a very, very good method. Because what it'll do is it detects where it needs to, and it'll do it versus you having to kind of guess. Again, a part like this is really kind of easy to guess where you need to apply it. But if you're dealing with more complex parts, then it can be a little bit trickier. Again, I guess you could always run a preliminary study and then figure out where the areas are of high stress, and then kind of go back and do it that way. But H adaptive literally handles that all for you. P adaptive, so pretty much the key thing with H adaptive is why it's called H adaptive is it's because it's shrinking the element size in certain areas. So it's adjusting the element size. That's what makes it H adaptive. Because again, H is another word for element size or another symbol for element size. P adaptive works a little bit differently. Again, the goal is still the same, is to try to make a more accurate study or give you a more accurate study. What P adaptive does, if you recall from the first session when I was kind of talking about the different orders of elements, like a draft quality versus a, what is it called? High quality mesh. So obviously draft quality is a first order element. So it's, it's a linear element versus a second order, it can do a parabolic displacement. So what P adaptive will do is it will, in the entire model, it will keep, it'll again still run different studies, or in this case for P adaptive, they call them different loops. And what it'll do is it'll keep increasing the element order. So it'll start with a second order. And again, you can adjust all of these. So if I'll go, well, I'll kind of get into P adaptive later on after I discuss H adaptive a little bit more. But yeah, P adaptive pretty much is going to increase the element order over, increase it one by one until it actually, again, it has some sort of convergence. P adaptive, I will say, is not used as much as H adaptive. H adaptive is a very, very useful one. P adaptive, again, it has its uses. I don't think I've actually even touched P adaptive since I actually was doing stuff in my CAA class, because there's really nothing. Again, in most things, you're really concerned with the high stresses. You want to concentrate on certain areas. You don't necessarily want to have a high order element all over the part. But again, there are probably certain applications where P adaptive are useful, but H adaptive I would say is used more than P adaptive. So starting out with H adaptive, so if you want to do an H adaptive study, you'll go here to H adaptive. And again, if you've taken CAE, this is probably a bit of a review. But so your H adaptive, so your target accuracy. So the first one when you're in your H adaptive, again, when you have a stress that's going up or whatever it is, it's going to look for convergence. And again, from calculus or whatever, you'll know that pretty much one test for convergence is to try to figure out if you take two different iterations of something, figure out what the discrepancy between them are. And then what you can do is from that, if that discrepancy is within a certain amount of, let's say the first stress is, let's say 100 megapascals, then the second, if you run the study again with a finer mesh, now it's 110, that would be like a 10% difference between the two. So if that difference is small enough, in this case, if the target accuracy is 98%, which means your result has only changed by about 2%, then it'll treat that study as, it's converged, and then it can stop the study there. So that's one way. So that's a very good slide. If you need something a little bit more accurate, again, not every time, depending on the part, can it actually hit a certain accuracy. So if you're having problems where it can't reach a certain accuracy, gotta kind of always lower it down. But again, if you lower it down too far, then it kind of defeats the purpose. But that is kind of, you can kind of lower that down. But default is 98. I'll usually keep it as 98. Again, you could go all the way to 99. There is no such thing as 100 because, again, if you make it finer, you're always going to have more accurate stress. But yeah, 98 is pretty typical. So accuracy bias, I usually just keep this in the middle. Again, if you need more accuracy on a local area versus globally in the part, you can kind of adjust this. But typically just the in-between value or intermediate value would be fine. So this one's a kind of an important one. So maximum number of loops. So what this will do is, let's say for some reason it can't hit this 98% accuracy for some reason. Let's say you have a sharp corner like we looked at last week, and literally as it keeps increasing the element size, or decreasing the element size, you're going to keep getting a higher and higher and higher stress because you have that stress concentration there. So no matter how many iterations it does, and it can make the mesh as fine as it wants, you're never really going to converge. So this will never stop trying to do it. So this is what this maximum number of loops is. So the maximum number of loops pretty much says how many times do you want to rerun the study, or automatically having the H-adaptive rerun the study without, how do I put this? Without actually converging. So if it converges after the second loop, it's going to stop at the second loop. But if it takes maybe 3 or 4 different loops to converge, then the maximum number of loops it can perform is, in this case, 3. Sometimes I'll up this to maybe like 5. Again, if you have a huge study, then the more loops, it's going to take a lot longer to run. But that's just kind of, if you're getting a study, especially if it takes a long time to run, and if you're not, again, if your convergence is not 100%, if you're like, maybe I'm shooting for 98, but if it gets 96, maybe that's fine. Then you can kind of dial in the loops, like up or down. Mesh coarsening, this just pretty much means if you have like an area that has very, very low stress, it can actually make a mesh coarser there. Typically, though, I'll leave this off. Again, this is a bit of personal preference, because if I have like an intermediate mesh everywhere, it's not going to take a tremendous amount of time to run the study with that mesh. So I don't really need to get less accurate results everywhere else, even if I'm interested in one area. So I'll typically leave that off. But again, you can kind of play around with that on or off. Okay, so from there, that's literally all you have to do to set up the H-adaptive. It's really, really easy. Typically, you can just leave even the default values. So from there, what we can do is I'll just hit OK. Now, once you have that H-adaptive, again, I just named the study H-adaptive. This is not designating that I've actually specified H-adaptive. So right now, you're not going to see any real change in the study. This is just the property. So this is going to come into effect when the study actually runs. So the next thing, again, I already have my fixtures and my loads. But again, if you didn't have those, you'll go ahead and apply them now. And so let's go and do the mesh. So the mesh, you still need to create a mesh for a H-adaptive study. You can't just put H-adaptive and then just say not do a mesh or anything. So I'll do a mesh, and again, I'll do like again an intermediate mesh, kind of like we saw before. So you still do a mesh, and this is pretty much, when you're creating this mesh here, this is your kind of your baseline. So it's going to start with this mesh, and then the H-adaptive is going to go from here and make it finer in certain areas. Again, if you have that mesh coarsening, it'll come in areas that are not super fine, or it can make areas that are, don't have a lot of stress a bit coarser. But again, there's like 2 elements across here. I don't really want it to start doing like maybe 1 element across, because then I might start losing accuracy here. So again, I'll stick with this and then have it kind of make it finer from here. Okay. So with H-adaptive, literally that's all you have to do. You do your mesh, the rest of the study is the same, then we can go ahead and run. Before I actually run it, what you will actually see is you'll actually see it run every iteration. So you'll see if you once you come up here and you start seeing your stress pop up, it'll keep running it, and you'll see the stress actually after every iteration it'll actually display the stress. Depending how quick they run, again, sometimes it's fairly quick, but you can kind of get a general thing of what your kind of how your stress is kind of differing between studies or between iterations or loops. So what I'll do here is go here and just do run, right click, run. Okay, so one thing, it's giving me an error there. So one thing, H-adaptive does not like a blended curvature-based mesh. It only likes a curvature. So if we go back to the mesh here, so we go to create mesh, you can just go here and then just do a curvature-based mesh. Again, you can play with these as well. Standard mesh is pretty much, if you don't have any curves or anything, the standard is probably fine. Curvature is a little bit better for curved surfaces. Blended curvature is fairly similar to curvature, but it has some differences. And so pretty much from there, the H adaptive, obviously, if it needs to use curvature based, we'll just let it use curvature based. So we'll do that. Okay. So we have our mesh. Our mesh looks a little bit different than the other one. So I believe what the blended curvature based mesh actually is, it's a combination of a standard mesh. You can kind of see up here, it looks a little bit more, I would say kind of a little bit more disordered. Versus like the standard mesh is kind of very ordered in the areas that aren't curved. It kind of blends the two together. But in this case, this won't really affect much right here. So we'll go here and let's go and run. So again, keep an eye when it's running on the stress as it starts going up. So we'll go and run. Here's our loop 1 of 5. So 48.61, 49.53. And if it hits it, it just actually hit hit our 98% after only 2 loops. So then it'll give you this message right here. And it'll actually tell you we've hit the adaptive accuracy of 98.03 whatever percent. So you can, if you want to have more accuracy than this, if it hits it really quick, then you could literally up it to like 99% if you want. And I might do that just to kind of show what that'll look like. But that's where H adaptive is really, really nice is because if we actually look, let me go here and actually see if I can show the mesh. You can kind of have an idea of what the mesh looked like before. Where is am I under the wrong menu here? Let's see. Show mesh, there we go. So you can kind of see what the H adaptive did. This area here, again, this might be a little bit easier to look at on the recording because you can kind of switch back and forth between the like when it was just a regular mesh, but you can tell it kind of find this mesh up quite a bit here. I wouldn't say quite a bit, but a decent amount. So that's the H adaptive. So what I'll do is let's go back and let's try to, since it was really, really quick, let's go back to properties and let's see if we can up this H adaptive all the way to 99, which is the highest you can actually put it. So we'll do that again. I'll leave 5 loops. So we'll go there and hit OK. Again, everything is still there. The mesh is still there. Just because I modify the H adaptive, again, what I will do, this has actually modified the mesh. So what I will do again is I'm going to do a new mesh just to kind of start it from scratch. Again, if you already have a mesh that's fine and it's doing the H adaptive, you could literally do another H adaptive already starting with the finer mesh, which is there's some advantages of doing it that way. If you need to run additional studies, you don't have to have it, redo the previous refinements. So what I'll do here is let's go back here and let's just do a mesh. I do not want mesh advisor. Let's close that. Mesh advisor is one of those annoying things that I always click on and there's probably some use for it, but literally I'll just usually go right into the mesh. The advisor kind of tries to walk you through it, but usually it takes more time than just doing it manually. So again, we're at curvature. I'll leave it there and we'll do that. And this will kind of be, so that's what it started out as. And then again, let's go ahead and run the study. So again, these are probably gonna go through pretty quick. 48.61, 49.53. It's going on the third loop, 50.117. And we're at, I think, our 4th loop. And let's see our 5th loop. Okay, so I don't think, it didn't give us the message. So even with that, I don't think it actually reached 99%. Again, you can kind of go through and kind of look at the different things and figure out what the discrepancy is. But again, this is a really, really quick study. And then if we go back and actually show our mesh, kind of see how much it actually refined it. So it's doing like an automatic mesh control. Again, it's doing some refinement over here, um, and over here. So you can see it's refining it in different areas that it feels it needs to. And again, so I did like what I did obviously earlier with the mesh controls, I actually did some refinement in these areas. And I literally said there's probably no reason to do it. And that's why obviously the H adaptive is not doing anything there because there's really no stress there because this entire back face is fixed. The stress there is extremely low. Um, any questions on H adaptive or mesh controls or anything like that?
Is there any reason you'd rather use the first method, the mesh controls, instead of H adaptive? Because it sounds like H
Um,
adaptive is just like a much better way of
that
using
is
mesh
true.
control.
Yeah, that is true. So yeah, typically, the only way or the only reason I would say you might want to do what is it called? You might want to do mesh controls instead of H adaptive is first of all, if you're just trying to run maybe a quick study and you don't want to have to set up the H adaptive, again, the H adaptive hardly takes any time. If another reason is maybe if you just want to find it in one area, maybe you don't want to have it run several iterations. Maybe you just want to have a really, really fine mesh in one area, then you could use the mesh control. So the mesh control gives you a
Mhm.
little bit more control kind of over the study. Whereas the H adaptive is more, you're kind of leaving it to SolidWorks simulation to kind of decide. Um, does that kind of answer your question?
Yeah, it does. Because
Okay.
like I guess when you have more parts, maybe H adaptive wouldn't be the best.
I mean,
Um,
yeah, even with parts, it wouldn't be a big, I wouldn't say it wouldn't be a big
Definitely.
deal. So again, it kind of just depends. Like some people really like I would say it's more of a personal preference.
Mm,
Because some people really, really like to have complete control over the study, versus they would say if I do the mesh control, I know exactly what kind of mesh I have everywhere or in certain areas. Whereas with the H adaptive, again, you can go after and kind of look at what it's doing with the mesh. But some
mhm.
people may not like that. Again, I personally I like H adaptive quite a bit. Because it's a quick way. I don't really have to go in and do any mesh controls. It'll just do it. So I personally use H adaptive most of the time, unless again there's a certain situation where I'm like, really want to find mesh right in this area. So if you notice here, let's say see only this area is really, really fine. Maybe if you
Yeah.
wanted like a fine area on the entire thing, again, it's probably really not necessary, but if you want that control, mesh control can kind of give that to you, where H adaptive is kind of leaving it up to SolidWorks to kind of decide. But yeah,
Hmm.
so it's kind
Got it.
of I would say it's kind of a bit of personal preference, but yeah. Okay. Any other questions?
No, that was all for now.
Okay,
Thank
perfect.
you.
You're welcome. Okay, so that's H adaptive. So yeah, again, H adaptive, I really, really like H adaptive because it literally it makes your job really, really easy. You don't really have to do much. You can get really high accuracy without really having to spend a lot of time, number one. Because again, most times to get higher accuracy, if you don't use an adaptive method or mesh controls, you're gonna have to just make the entire part really, really fine. And again, I mean, a part like this, even when we made it really, really fine, it was like, I don't know, 10 seconds of runtime. But if you're dealing with something that has, I don't know, 10 million elements or 100 million elements or something, or maybe it's an assembly or whatever, yeah, you might be dealing with hours or days at that point. So yeah, with mesh controls, it's really, really nice. And H adaptive. Okay, so next I'll get into a little bit of P adaptive. Again, I don't use P adaptive pretty much ever. Again, there are probably certain situations depending on the type of deflection you're having. If you're having a deflection that could be better modeled with a higher order element. But personally, I think, and this is personally speaking, I think H adaptive, um, the what is it called? The finer elements in the really critical areas, I think does a little bit better of a job, in most cases than P adaptive will. Because again, P adaptive is going to kind of do it all over the part. Um, so what we'll do here is I'm going to make a copy of this. So let's do copy study, and then I'll just call it P adaptive. And P also is why they call it P adaptive. So P is another word, like H is for the element size. P is the order of the elements. So that's why it's called P adaptive. So we'll do P adaptive, and we'll do that. Okay, so obviously very similar to H adaptive. Go to properties. Then we'll go to adaptive, and we'll switch over to P adaptive. So stop when there are different like criterions that it can use to stop on. Again, P adaptive is not something I use really, really often. But again, if you want to have more information kind of about how it calculates everything, you could, there's quite a bit of, obviously there's quite a bit of information online to kind of look at exactly how it actually calculates everything. Um, so again, so it's pretty much dealing with the strain. So say stop when the total energy strain is less than 1%, or change is less than 1%, or less, or less. Update elements when the relative strain energy is 2% or more. So it'll kind of update. So again, so technically with this, it is actually still kind of trying to figure out where the certain strain energies are higher, and it's going to try to adjust the elements in those regions. So I think I don't want to, I kind of want to correct myself previously, where it may not necessarily do it all over the part. It'll try to still figure out where certain areas need um, better, kind of better elements. So again, starting P order, two, again, you can start, I don't think you can even start with one. Yeah, you can't even start with one, because if you're doing a P adaptive, there's really no point of starting with a draft quality mesh. Maximum is 5. I think 5, yeah, 5 is the maximum. So and then the maximum number of loops, again, it's going to try to run it. The difference with a P adaptive, and this is kind of one reason I don't personally like P adaptive as much as H adaptive, is I love the thing with H adaptive where as it's running it, you can actually see the stress changing through within the loops. P adaptive does not do that really, unless they've changed something since the last time I've used it. But the last time I used it, I think in SolidWorks like 2022 or something. It's not, it'll pretty much run everything and just give you a picture of it. But yeah, so pretty much that's what you do for P adaptive. Hit OK. Very similar. Go here, go to create mesh. Um, Again, I wonder if I do this and try to run it with a blended curvature. I wonder if it'll give me an error or not. We'll see. No, so actually P adaptive I guess can work with, so it'll just kind of do loops like this. It won't actually, and then it'll just give you a thing. So I think it did 2 loops. Again, I'm not sure if you can see the little window that popped up, but it has a little bar and it'll tell you which loop it's on. So it's 49.14. What is our H adaptive? Let's just for comparison. 50 versus the P adaptive is 49. So again, they're still relatively close. So again, they both act similarly. Both of them is the goal of both of them is to try to increase the accuracy of the results. It kind of just depends on what the preference is. But if you will notice after doing this, if you go ahead and look at the mesh obviously looks identical. You're really not going to tell a difference in the mesh with the P adaptive because it's pretty much just how the mesh can actually deflect. So yeah, so that's pretty much P adaptive. Again, I would say most of the time you'll end up using H adaptive, but if you need to use P adaptive, that's how you can kind of use it. Any questions on P adaptive? Okay, so that's a lot about meshing. So what I'll probably try to get into now is what if you're working with a either kind of an assembly or you're working with a part with multiple bodies in it. Um, so I'll try to start getting into a little bit of that now. So I'll just go and save this model. But that's pretty much, I would say that's a pretty good overview of all the different things you have with meshing. Obviously, you can just manually do it. You can use mesh controls. You can use H adaptive. You can use P adaptive, kind of to refine the mesh to your liking. So next, what I'll do is let's go ahead and just do a new part here. So I'll go here. Let's do an inch. Let's just do a metric part. Okay, so what I'll do here is I'm going to try to create a part that actually has 2 bodies, just kind of show, because the next thing is going to be contacts. So what if you're not always lucky enough to just do an analysis on one single part? Sometimes you have an assembly, or you have a part with multiple bodies in it that are kind of representing kind of an assembly, or something similar to that. So what I'll do here is let's go on the right plane. Let's try to model something up here real quick. And what I'll do is I will let's see here. I'll just kind of draw a couple rectangles. And I'll just grab this midpoint here, holding down Control, make those coincident with the origin. And again, I'll grab another rectangle over here. And there's several ways you can do this. You can either just grab this here until you get the coincident, or you could also make this line and this line collinear. I will make these equal. Again, you don't really have to, but it just kind of makes it a little bit easier. And let's try to get some dimensions here. So here, let's just say it's 25 millimeters wide by maybe, I don't know, 15 millimeters tall. That adjusts both of them. So what I'm going to do now is let's go ahead. Let's go to features. Let's go to extrude. Since this is what's called, you have several contours inside one sketch because you have several closed entities. So what I'm going to do is I'm going to do these as separate extrude features so I can actually keep them as separate bodies to kind of show connections. So I'll do that, and let's extend this out there, like maybe like 200 or something. Yeah, maybe something like that. Maybe 250. Yeah, something like that, maybe. So we'll do like 250, or actually, no, 250. There we go, something like that. And so we'll do that for the first one. So now I'm going to use one sketch. Again, you could sketch these as two separate sketches and then still extrude them separately. In this case, I'm using that selected contours to actually use one sketch and actually use it for several features. So when you have the same sketch, you can go under the feature, click on the sketch, and then go back to features and extrude again. And again, use your selected contours. Sometimes this is up like this. You might have to expand that. And then go here, and then I'm going to make them the same length. So this is kind of like maybe like a beam, but you've got like two pieces that are maybe glued together or fused together or something. So you can do that. One thing when you're dealing with separate bodies, there's a really important checkbox here that you want to deselect, which is merge result. So what merge result will do is if two bodies are intersecting or they're touching, it'll merge them into one body. Most of the time, this is what you want when you're dealing with a part. You don't want every feature to be a separate body. But in cases where you're trying to work with things like this and you want to have two separate bodies, you want to uncheck the merge results checkbox there. And once you start doing that, that's what's called multi-body part modeling. You have several bodies within the same part. And there are, even in modeling, with simulation, obviously there are advantages. With modeling, there are advantages as well, because you can do different things. You can combine them together. You can subtract one from another. So there is quite a bit of power that comes with multi-body modeling. So I'll do that. I'm going to uncheck merge result. If you don't uncheck it, you can always, like, if I accept it for some reason, that's what it'll do. But I can go back in here and then uncheck merge result if I forget it for some reason, which I do quite a bit because it's an easy thing to forget. But you'll kind of know instantly when you forget it. So now you have two separate bodies. Again, if you don't have this set on by default for your solid bodies, typically if you only have one body, this folder won't show up. There is an option that it'll always show up. But right now it'll actually show up if you have two or more bodies, and you can actually see your different bodies. So that's one body on the top, another body on the bottom. Okay, so what we'll do now is let's do a study kind of on this. Let's set up another study and kind of simulate this and figure out, because again, we have two separate bodies. We have to kind of tell SolidWorks simulation how we want them to interact. So that is that's kind of a big one. Okay, so what I'll do now is, so let me go and save this part first. Let's go here and let's call this like sample 2 or something. Before we go any further, any questions on multi-body modeling or anything I did in the sketch or anything? Okay. So moving on to SolidWorks simulation. So again, let's go to simulation here. Again, right now I have plain carbon steel for the entire part. Again, I could leave them both as the same. I'll probably in simulation define separate materials just to kind of add an extra level of complexity so you can kind of see what it'll do. But so yeah, so I'll go to SolidWorks simulation. Let's do a new study. This is going to be static. Now let's go ahead and hit accept. So the first thing is under sample now, you have actually two bodies. They're both solids. So they're both going to use solid elements. So what I'll do here is, let's see if I kind of bring this out a little bit. So they're plain carbon steel. So let's just make it a little bit more interesting. If I can get this to expand out. So let's make the bottom one, let's see here. Let's make the bottom one aluminum. Just to kind of play with some things. Again, you could do these as the same material, but this is where you can actually, if I can type 60, 61. Let's do T6. That's very, very common alloy of aluminum. Okay, so something like that now. So now we've got aluminum bar on the bottom. And with composites, when you have two different materials, it can sometimes get a little bit tricky with SolidWorks simulation. So it definitely you want to kind of check your results if you need to, if you feel something is not 100% right. Okay, so we have this. So now what we'll do is I'm just going to deal with this as like a simple beam. I'm going to fix it on this end, and then I'm going to apply a force over on this end. like, and so it's going to be kind of like a cantilever beam. This end is going to deflect kind of down. So what I'll do here is let's start with I'm going to apply the fixtures and loads, then I'll come back and talk about the interactions. Let's go to fixtures. Let's go to fixed geometry. Again, I'm just going to put a fixed constraint on both of these faces. Again, since these are separate bodies, I wouldn't say you have to put a fixed constraint on both of these faces. But if they're not, and I'll get into this a little bit later, if they're not interacting with each other, if you don't put a fixed constraint here, this will just fly out into space unless this body somehow is preventing that from happening. So I'll kind of show kind of a couple different things with this. So I'll do a fixed constraint there. And then what I will do is, let's see here. Then what I'll do is let's go and apply a load. Let's apply a load on maybe both of these faces. Let's see, 1,000 newtons. I'm going to do total here. I don't really want per. So if you select several faces, if you have 1,000 newtons and you have per item, everything you select, if it's an edge, if it's whatever, is going to put 1,000 newtons on it or whatever you specify. So that's something to be careful with. You can end up getting double the force you want. So that's just something to be a little bit careful of. So select a direction. I can just select this top face here and then kind of play with those and maybe kind of reverse. Let's reverse the direction. Reverse. And again, I have to put 1,000. And it's going to be total, again, not per item. Okay, so something like that. So probably the rest of the session, I'll probably be just working on this and just looking at different loading configurations and different things, because I think there's a lot to kind of learn from a setup like this. Okay, so we have something like that. So the first thing I'm going to do is now I'm going to kind of jump into interactions. So interactions is pretty much, so there's connections and there's interactions. You can add different connections. I'm not going to really go into connections today. I'm going to mainly talk about interactions. So connections is like if you have a bolt, there's different ways of approximating different things. Maybe you have a bearing in something. If you don't want to have to actually model the bearing, there are ways to kind of use those connections. But component interactions is pretty much how different components interact with each other, or in this case, different bodies. If you're in assembly, this is very, very similar. Same idea, so your component interactions. So right now, by default, when you start a simulation, there is what's called so the global interaction is the overall interaction, and by default, it's what's called as bonded. And they're saying it's meshed independently, so they're meshing them independently. So pretty much what the bonded interaction means is it's pretty much like they're glued. So if they're touching each other, they're going to be glued together. So in this case, it's like in this example, this face that's in between these two, because you got these two bars, it would pretty much put a whole bunch of super glue or whatever kind of glue you have and glue them together. That would kind of be what a bonded um, component interaction or bonded interaction would look like. So we'll start with this one. Let's just kind of look at what we're dealing with. So what we'll do here is let's go to mesh. I'm gonna check here real quick. I don't think I have any adaptive on. I don't really need adaptive. Yeah, we'll just do none. Yeah, okay. Okay, so let's go to a mesh. Create mesh. I'll just kind of do something intermediate. Maybe I'll bump it up a little bit. And let's see. Blended curvature is probably fine. Again, I could probably just do a standard. Actually, I'll just do a standard mesh on these because there's really no curvature. So that because usually the curvature based meshes, they usually take a little bit longer to generate than the standard. But yeah, so we'll just do that. And we'll hit accept. Okay, so we've got, what is it? 1, 2, 3. We've got 3 elements across the thickness on both of them. That's good. And let's just go ahead and run this. So let's go and save again real quick. And let's go ahead and run the study. I can run it from up here as well. So let's go and run. Should be a quick study. Okay, so, and let me do this and where am I? Let me switch this to floating. So we'll do that. Yeah, floating, and then I want this as megapascals. I probably should have copied one of the other studies. Actually, I can't copy another study because this is a new part. So let's go megapascals. So we'll do that. Displacement, same idea. Let's go to chart options and go floating. Okay. So let's see here. So what I'll do is I'm gonna actually rename this. I'm gonna call this bonded. So those two are pretty much bonded together. Okay, so that's the stress. Now, when you're looking at bonded, if you notice here, like I kind of said, they're glued together. So when you're looking here, one is not sticking out further than the other. They're moving pretty much as one body, although they're two still separate materials. Another thing that's also intriguing or interesting to look at, especially since this is a composite structure, is if you notice here, there's a lot of stress up here, and there's a lot less stress here. Um, so the reason for that, again, I don't think these have yielded. Again, since you have two bodies, you're not going to get a yield strength necessarily, or you've got two different materials, so you want to definitely check your yield strength. I will actually check that real quick. 661 probably has the lower yield point. Yield strength is, I'm going to go here and just put this in megapascals. Yield strength is 275. Yeah, so even the aluminum is really, really high. And if we go to, so if I cancel that and go to plain carbon steel, so that's something to kind of keep an eye on. It's nice when you only have one material because then it'll tell you the yield strength. You don't really have to look anywhere else. But you should know the yield strength of your materials anyway. And just kind of write it down or something. And the other one is yield strength 220. Yeah, so we're like have a factor of safety of above 2. Okay. So another thing, you have a lot of stress here. You don't have a lot of stress here. If you remember from strength of materials, or for those who haven't taken strength of materials, the more rigid body is going to actually take more load, or it's going to take more stress. So it's kind of like the opposite of kind of like opposite if you've taken circuits, the opposite of electricity. It's not the path of least resistance. The force is going to take the path of most resistance. So since the steel is stiffer, it's going to try to go through the steel until the aluminum. Pretty much, the aluminum is, think of it as kind of being a little bit softer, so it's going to be able to deform more, and then the stiffer material is going to have to take more of the load. So that's another thing when you're dealing with composites. These are again are metals, which are a little bit easier than if you're dealing with polymers. But that's something to kind of look at, just because you're just because you think you maybe run a hand calculation or something, and if you remember from strength of materials, there is a method, especially with stuff like this, where you can convert one material into the other. You kind of adjust the cross section. But again, you can go probably online and look that up if you're dealing with a composite beam or composite anything. So yeah, so that is pretty much a bonded boundary condition, or a bonded component interaction, bonded connection. Any questions about this study so far?
I have a kind of a question, but it's not really
Okay,
about the study. But
sure.
um, so you know how you made two different solid bodies?
Yeah.
Can you could you like how is that different from like assembly if you have two different parts? Or like
So that's a good question. So
yeah.
so pretty much an assembly, obviously it's a collection of multiple parts,
Hmm.
whereas so technically speaking, not much.
Yeah.
So again, when you're dealing with multi-bodies, you can't really move stuff around like in an assembly. If you have multiple bodies in a part, you're not going to be able to move them around. Like you're not going to be able to tell degrees of freedom and stuff like that in a
Hmm.
multi-body part because they're really all fixed in place. So for simulation, like literally, if I could model those as two separate parts, mate them together with like a coincident mate,
Hmm.
um, this study would be the exact same. So it wouldn't really change anything. So in this context, nothing really changes. Again, in this case, it's a little bit simpler for me. So sometimes I guess maybe this is one way of putting it. If you have something simple like this, it's sometimes a little bit simpler just to set it up as a multi-body part,
Yeah.
versus having to do an assembly. Again, it comes down to a little bit of personal preference there. But literally, there are advantages. I would say obviously assemblies do have their advantages. Again, being able to visualize motion is a big one. Again, you can
Hmm.
move bodies around, but you have to move it with a feature. You can't just click and drag and just kind of move things around like you normally would in an assembly. But again, if you want to kind of subtract one body from another, you can do that in a multi-body part. Again, you can do something similar in an assembly as well, but I would say it's not as straightforward.
Yeah,
Uh,
I'd actually this is really helpful because I feel like I've had this problem before
right?
and it would have
Yeah.
helped me.
Right,
Uh,
right. Yeah. So yeah, multi-bodies are really, yeah, they're really good for kind of um if you need to do, again, multi-bodies more of the time they're useful in simulation, but they're also extremely useful in just modeling. I use them all the time because it's a lot of times you may want to um like let's see, a good example is if you've ever had a part where you're putting a fillet and the fillet is trying to wrap around or something, and you don't want it wrapping around, you could always split that into two bodies, put the fillet on, and then merge them back together. The two bodies, the fillet cannot go into a different body. It has to, the fillet, specifically for the fillet tool, the fillet can only be applied to one body. You can't apply fillet, you can't apply the same fillet on two different bodies. You can apply separate fillet features, but that same feature can only apply to one. So there are some really, really good applications, I would say, of multi-body modeling. Um,
So if you're using the connections, is it pretty similar to like an assembly when you're doing a connection, like a or
it's
is it
showing like
pretty
in the
different?
simulations, like in the
Yeah, like
simulation.
yeah.
So with that, not really. So I'll yeah, let me get into that. So is that kind of answer the first question I got? 'Cause that's what I'm gonna get into next about the connection. So you'll kind of see,
Okay.
it's not really. I would say yes and no. It's not really what what you're thinking of as like a mate. It's not
Mm,
really. It's more of in the context of the analysis. So you'll kind of see. So let me get into that now.
mm, that makes sense actually. Yeah.
Yeah. So we'll get into that now. So what I'll do now, is obviously let's go. I'll just do a let's do another. Let's do another. Let's just copy the study. And I'll just call this contact, which is another spell. Okay, contact. Okay, so we'll call that contact. So this is another type of connection. So in this case, a lot of times the bonded or the global interaction is not exactly what you want. Maybe you don't want them bonded. Again, you could just go in here and you could either suppress or delete it. Again, one thing with so there's two different types of interactions. You have a local interaction and a component interaction. You also have a global interaction, which is just the overall of the entire part assembly, whatever you have. So kind of the thing is whenever you specify a local interaction or something that's in a localized area, that's always going to take precedence over a global interaction. So kind of very similar to like mesh controls or something like that. You have your general mesh, and then if you specify a mesh control, that's automatically going to supersede the whatever global mesh you actually specified. So very, very similar here. So again, you can delete this out if you want to. Again, if you specify something like local, it's not really going to matter too much. Before I get into this, though, I will show another trick is because what I'm going to try to do is the interactions, these are interacting along this face that's in between the two of them. So it can be a little challenging to actually be able to select that face. So what I'm going to do is another advantage of multi-body modeling is you can actually right click here and do a new exploded view. So very similar how you would in an assembly. So what I can do is I can just bring one of these up like so, hit accept. And now I have an exploded view that I can turn on and off. Now, one thing here, this exploded view is really just a visualization. When you run a study, even if you're looking like this, they are not separated. They're still in the original position. So they're still touching each other. It's just a way that you can visualize. You can also select faces in between, if that makes sense. So that kind of, it's a really easy way to select faces that are maybe common between two bodies. Okay, so what we'll do now we'll go back to our study. And what I'll do now is let's go ahead and specify if I can actually, why can't I do, why is it not allowing me to, if I do the exploded view, it's not gonna allow me. Okay, so maybe, again, this would work, this works in assembly as well. So let's try to do a, let's see here. Um, okay. So let me try to do a connection real quick and see if we can still leverage that exploded view. If not, if that doesn't work for some reason, I will do it a different way. Um, so what I'll do here is let's go to component interactions. Let's do a local interaction. And let's see if I can, from here, can I try to, that's not what I want. Okay, so we'll try to do that. Another way you can also try to do this is, yeah, so apparently the exploded view is not working. That might work more. The thing with, when you're dealing with exploded views in a multi-body part, it's not as I would say it's not as robust as dealing with multi-body or as an exploded view in an assembly. You don't have all of the same kind of tools that you do. So what I'll do is I'll kind of change this up a little bit. So I don't really need that expletive here since it's not working. Um, so what we'll do is instead of that, I'll use another kind of nifty tool. Um, and I will do this. So let's go to our component interactions. Let's do a local interaction. Again, you could do a local or a component. The difference is a local is you're usually selecting faces, edges, stuff like that to apply the interaction to. A component, you're just saying if this component ever interacts with this other component, do it that way. I'll probably actually, if I'm trying to do a contact, I'll probably do a component interaction, but I want to show how the local interaction works as well if you need to do a local interaction. So contact, you have some different things. Contact, bonded. If you do a thing between two faces that is bonded, it's the same as pretty much the same as the other one, like the global that it did before. You also have free, which means there's they don't interfere. They can literally go through each other. There's not much. Shrink fit and virtual wall. I'm not entirely sure. These are not two that you use very often. But yeah, I might get into some of those maybe in a later session. Okay, so for this, let's see if we go here. So set ones, you're going to select two sets. So what you'll do here is I'm going to use another really nifty tool that's called select other. If you right click on a face and hit select other, you can actually, it'll hide that face and you can actually select a face of different bodies. So what I can do here is in this case, I want face of edge boss extrude 1, which is going to be the top. So I can select that one. And then for my second set, I can do the same thing, select other. And then in this case, I want the one from the boss extrude 2. And then what I can do is do contact. Again, you kind of mess with some of these with the gap, like if there's a gap, what do you consider contact and things like that, but I'm not going to really worry about too much of that. So that's you can do a local interaction. Again, you can also do a component interaction where they're compact or where they're contacted. So what I'm going to do here is you're going to see a little bit difference of a difference here, and then I'll start actually kind of playing with the loads and seeing kind of really going into how the contacts kind of are applied. So the first thing let's do, or what we can do here, let's do this. So what I will do is, let's see, let's go and just run the study again. So the mesh should be fine. I don't think I changed. Oh, there are some contact. Yeah, I'll go and remesh just to be safe. I'll just do this. I'll just do a mesh and run. So now this is with a contact constraint. Again, contact, you can see this is taking a lot longer now. A contact, so when you're dealing with contact, bonded is a lot simpler for SolidWorks to solve than a contact, because now contact, you got to kind of be careful of exactly how they're contacting each other. So when you start getting into contacts and different component interactions, this is what can really make your study, especially if it's an assembly, you can make it very, very long. So here's something like that where they're contacting each other. So again, remember, there's an equal amount of force on either one. And now what's happening is they are actually, the aluminum is deflecting more than the steel is. And you can see the stress now is very, very different. So in this case, the contact is really not doing much because they're kind of separating apart. But then what I'll do is I'll kind of go back and change it, kind of change the loads a little bit so you can kind of see. But any questions on this study specifically?
I don't have any questions, but I do have to go.
Oh, you're good.
Yeah, I'm sorry. I
Yeah.
really appreciate it though.
Oh, you're welcome.
Helped me
No
with a
worries.
lot.
Yeah, sounds good. So yeah, I'll keep going through this, and yeah, there's going to be a little bit more. I'll probably be wrapping up probably in the next 10 minutes,
Okay,
or
I'll
15.
go back and watch the video.
Sounds good.
Thank you.
Perfect. You're very welcome. Take care. Okay, so now moving on, what we'll do is let's move on to this. So what I'll do here is instead of doing, I'm still gonna do a contact, but instead of doing a contact with the force applied to both faces, I'm gonna kind of go and change it a little bit. So I'm gonna go to my force now, edit the definition, and I'm gonna turn off this force on the bottom. That's actually not what I want. Let me cancel that real quick. Let's go back to the force edit definition. So I'll go here and I don't want this right here. So the reason for this is now, if we're kind of looking at how this problem is getting set up, is this top bar is pushing through the bottom bar. They're both still fixed on the side. If I took this fixture out, then I would have an issue because now this is just going to fly out into space somewhere. They still have to be fixed or have some sort of fixture. But now this one is pushing through here. So they're not, because the last one I just did, the two bars, technically there's a contact, but they're really not contacting each other. This one is deflecting more than that one. So we're going to kind of change that around a little bit. So, and we'll go ahead and hit accept here. So now I just changed the loads. If you just change the loads, you do not need to do anything with the mesh, and you see the mesh is still fine. So all I need to really do now is just rerun the study. And again, contacts are going to still take a little bit longer to run. And again, this is one thing while it's kind of running. When you're starting to deal with contacts, if you can try to simplify the contacts, that will help. Like if you have a lot of unnecessary contacts where you really don't care about like two components interacting, you really are concerned with these other two. Let's say if you're dealing with an assembly or even a multi-body part, and you really don't care about these other ones, then you may just treat them as bond or do something to try to simplify them a little bit. Or if you can, again, this is not always possible. If you can just try to remove them from the study completely, just try to suppress those components. Again, that's not always possible because sometimes let's say if it's a linkage or something, you don't really care about the stress in that component, but it is affecting the other components in the chain or in the mechanism. So now this is what you're looking at with contacts. So you can kind of see where they are sliding. This one looks like it actually came into this one a little bit. That could just be because of the deformed result. Yeah, that was because of the deformed result because they should not be intersecting at all. So if I go back to deformed result, so you can see now they're not bonded. So like if you notice from the first time, now they can actually kind of slide along each other. So they're both like almost welded to the wall, but they can both nothing's really preventing them from kind of sliding on each other or pushing each other around. So that is a contact interaction. And again, you notice, so this is where I was saying, if you're noticing here, um, what's the word? The stress values, if you've kind of been watching as I've been doing this, between these different scenarios, the stress values have actually changed rather drastically. So this is where I can't understate the importance of context and just being able to set up your study properly and trying to figure out. So loads loads are usually pretty easy. Fixtures are a bit more challenging. Interactions can be even more challenging than fixtures, depending. So a lot of times you want to do something like this. Again, it never hurts when you're doing something like this. Again, this is a very simple part, so you can kind of see what the behavior is, but it never hurts here to actually go here and do an animate. Again, I'll stop it and do like maybe 20 frames just to kind of get a smoother picture. So this never hurts to be able to kind of see how they're actually behaving. Because in real life, again, you may not always see it deflecting this much, but you kind of have a picture in your mind of how it should deflect, and you want to make sure that simulation is getting that right picture, or getting that right scenario. Because if it's not getting the right scenario, then your study is really not doing much good. Okay. So we have that. So again, this is a little bit of composites and a little bit of, what's the word? And a little bit of kind of connections. Again, component interactions are very similar. So if I were to actually go back here and get rid of this local interaction and do a component interaction, let's go here and do a component interaction and then select between the two components. So this is sometimes a little bit easier if you've got like a common face. So do that and then do contact. Again, free, there's really no need. Well, I guess I'll probably simulate it in a second so you can just kind of see what free looks like. So we'll do a contact there, and then I will go ahead and rerun. So we're at 198.59. This should be very, very similar. Again, it'll still take a little bit. So the local is good if you just have certain faces, certain edges, or certain things that you want to kind of play with, and you want this to not intersect that or whatever. Component is a little bit easier if you just this component, obviously. Now it can, yeah, so you see it's identical. So one thing is I will say with contact. Contact is a very realistic condition. Because obviously parts, a lot of times, unless they're welded together or they're bonded in some way, a lot of times parts are not able, or parts or assemblies or whatever components component you're dealing with, they're not just able to kind of float through one another. Although, like if you worked in SolidWorks at all or anything, or you're starting out in SolidWorks, you'll probably notice, especially when you get into assemblies, you can drag one part like through another. SolidWorks doesn't really care. Obviously, in real life, that's just impossible. It's physically impossible. But like two objects cannot occupy the same place at the same time. So what'll happen is, so contact is a very realistic condition. Again, unless you have it bonded or you have some sort of you have something that's maybe it's welded all the way along here, or you have some sort of epoxy in between these two pieces, then a contact is probably not as accurate. So this is where you really have to kind of, as the engineer, you have to really kind of go in and look at how how do I think this is behaving? How is it attached? This is not always an easy thing to do, because especially if something simple like this is pretty easy to look at. Um, but other things, if you have a complicated assembly or a complicated mechanism, it's not always that easy to just kind of look in or look at it and say, how does this happen? Um, so context can be very challenging at times. Okay, so that's a component interaction. Um, Same contact. So again, in this case, I would versus having to do the selection of the faces and everything, I would honestly use the component interactions. It's just a little bit easier to apply. Again, but that is doing that entire component. So if there's part of a component that maybe is bonded and the other part is contact, then that's where you can use a local. Let's say, it was something that's like part of it is, maybe it's like a V, like upside down V. This part is contact. These two faces, you've got two like instead of these being flat or straight across, they're like that shape, a V. So maybe this side is contact and this side is bonded. So that's something where a component interaction would not really work in that situation, because what will end up happening is if you do a contact, it's going to do a contact everywhere. If you do a bonded, it'll do a bonded everywhere. One thing you can do is you could do a component interaction between them. Let's say call them bonded, and then you could go in with a local interaction and do, let's say, a contact. Again, a local interaction, kind of the overall, it's going to go from the global level to the component level to the local level. So pretty much the more kind of the smaller level, or the more in depth you are into the thing, is going to be the interaction that's going to take precedence. So local is going to take precedence over a component. A component is going to take precedence over a global. Um, okay, so let's kind of do a free component interaction, just kind of, and then I'll kind of wrap up here for today. First of all, any questions on anything here with a component, local, anything like that? Okay, so now let's go in and do a free. Again, I'm going to do this in the component at the component level, because there's really no need. It's just going to make it a little bit more challenging to do this at the local level. So let's go here, and then I can just modify this component interaction. Let's go and edit, and let's go ahead and do free. So free pretty much means they do not interact at all. Again, this is not entirely realistic in real life, unless they're just completely don't contact each other at all. But maybe you could use a component interaction between two components. Maybe you just don't want to ignore any interactions between those two. You don't really care if they intersect in the simulation. You're really concerned about something else. But if you're doing that, you definitely want to be careful to make sure that by neglecting that connection, you're not really impacting the accuracy of your results, or of your analysis. So let's go here. Let's do free intersection gaps. Okay. So yeah, and usually it'll tell if you need to remesh. So if there's something like that, let's go. The mesh will have this little caution symbol. So let's go here and let's just do a mesh and run. Again, the load is still only applied to this face here. So now that is what a free is. So this is obviously not realistic at all. You have zero stress on one, you have a lot of stress on the other. One is able to go right through the other. And if we kind of animate this, that's kind of what you're looking at. So that's what a free connection is, or a free constraint, or a free boundary condition. You'll hear a lot of these terms kind of used interchangeably. So again, this is not realistic at all. I mean, unless you're just trying to kind of do this for an example like this. So again, this is where you really want to be careful when you're kind of looking at again, the animate is really, really useful. Again, in this case, you didn't really even need to animate it. You can clearly see that one is like going nowhere. But if you do something like this and you apply like maybe a global condition of, let's say, free, and you're getting a result that looks something like this, then this tells you that obviously your free global result is probably not working too well. You may have to go back either at the component level, or the global level, or somewhere, and apply a contact, a bonded, something else, so this doesn't keep going through. Um, Again, typically at the global level, I will say this: unless you have something that's bonded to something else, I would usually just go at the global level and do a contact constraint. the reason for that is I don't have to really go down and do anything else. And again, if most of your components are contact, and in real life, I would say most components are contact unless something's, bonded together. But typically, if you've got like a bolt and a hole or something like that, that would be contact. They're not really necessarily bonded. You've got the bolt going through. If the part is trying to, deform the hole to get out of the bolt, or if you have, let's say, a hook and you're hanging something on it, it's technically a contact. They can contact each other, but they cannot penetrate. Contact condition is also, they actually changed this, I think. I forget which year of SolidWorks. It was rather recent when they changed it. A contact condition was also what was previously known as non-penetration or no penetration, meaning that one body, one part, one whatever cannot penetrate another. So sometimes you'll hear people call it non-penetration. That's what they mean contact. Because it was something that's what they used to call it in simulation. That then they changed it, I think, within the last few years, I would say. So you'll hear a lot of, if you watch any videos on YouTube or watch any things that are a little bit older, you might hear people talking about non-penetration, and you might look in your SolidWorks and not find a non-penetration. That's a contact condition. Okay, so we have that. And then again, how I would actually set up this study if I'm trying to do a contact condition, so I'm not doing bonded, what I would do is just delete this. And what I'll do here is I'll go up to the global, and I can actually edit the global as well, and I can just do a contact. This is probably the easiest way to do this. If most of your parts are just contact, put a global with a contact, and then if there's certain things that are bonded or free or something else, then you can go in individually, either at the component level or at the local level, and kind of, adjust what you need to based on the different components and how their behavior is acting in real life, or how you would assume they would behave. So I'll do that. I'll do a contact. Again, I'll do a mesh and run. And this should obviously, at this point, I've done probably 3 simulations that are identical. The contact at the local level, the contact at the component level, and now this one, the contact at the global level. In this situation, all 3 of these are identical. So again, you're still getting that 198. So yeah, that is literally exactly the same. But yeah, so that's kind of an overview of pretty much interactions. Again, you can go into, then at some point probably we'll go into connections. But for interactions, this is at least at this point, so far what I've covered is this should be enough to give you pretty much a general idea of pretty much how to run I would say a wide range of simulations. Single part, single body, multi-body, composite. Again, just make sure your contacts are right, make sure your constraints are right. Again, that's something that, it comes with practice. So you just kind of imagine in your mind what you would think it's going to do in real life, then try to simulate it and see if it's giving you that correct behavior or the behavior you're expecting. If it's not, then try to figure out, is the simulation correct or are you correct, and adjust from there, until you can kind of get the behavior that you're expecting. Okay, any questions on interactions or anything? Okay, so I'll probably stop here for today. So again, I would say this is a good overview of mesh controls, adaptive methods, and connections. So, and then yeah, I'll kind of keep going next week with some more things. But yeah, so this is connections and mesh and you know mesh controls and H adaptive. So yeah, so I hope that was helpful. And if no one has any questions, that should probably be good for today. Okay, so everyone have a great day, and then I will see you next week.